Greetings programs, welcome back to Stegosaurus Studios. My name's Mike and this is the shop. Today is Pit Droid episode number 7. I'm going to talk about quite a bit of changes to the left wrist testing apparatus, and then we're going to delve into something called the CANbus, which it turns out has nothing to do with moving school children around. Okay, let's see. What am I talking about here? So discombobulated here. So in episode 6, which was the last episode, I had a prototype wrist, and I was moving pulleys by hand as a test. And that test uncovered a whole lot of flaws. And I'm going to actually go over the changes that I made both to the wrist design and, more importantly, to the tensioning system and the bracketing that holds everything together. So let's talk, I guess, the wrist design first. I didn't. There weren't too many. There's just some small, very cosmetic changes on this, which I don't need to go over. Really, the important thing though was the creation of this little piece, which doesn't look like much, but basically it goes in right here, snaps into place, and now the wrist is locked. It won't move, and that is going to be so useful when trying to thread those fishing lines through and get it tensioned up. Because I don't have a spare set of arms and hands to hold it in place. I had my wife help, and I'll probably still rope her in on some of this, but that's going to help a lot. So that was the big change. And then I think on the last one, I didn't have the full forearm, so this shows now the full thing. I still have not redesigned the elbow. I decided I wanted to go ahead and do a full test, a better test than the hand done one, and I'll talk about what I'm going to be doing here in a second. So now let's talk about the changes to the bracketing system. So that was a dog's breakfast last time, and so this was the old bracket, and I got this from RO Technic. I had his link in the last video. And then, so this is the bracket. It holds the pulleys came up through here. And then these little slots here were part of the tensioning system. And these little towers were intended to slide back and forth to provide tension. So basically, the line comes through this hole here, and there's a little hole in the back. So the line goes through. There's a screw that goes down through the middle and then goes through the slot in the plate, and you put some sort of nut on the back. The problem with that design is once the thread is through, you can't put a screwdriver down in there to hit the screw. So you're kind of trying to tension it, from the backside, which is another problem. And so I was like, okay, that was a problem. And then the other thing is these tubes were just sat in there. And when I was trying to get it assembling, they kept falling out. So basically I've come up with a completely new design. I'll talk about what this is here in a minute, but so the first thing is I now have these compression fittings right here that are made for the 4mm tubing. So once they get put in there, they'll be captive and they won't be falling out. The thread will go through and come out the back, just like before. The tower then slides back and forth, but you'll see I've put it into a 3D printed and designed this channel that it fits in. So it's captive, it's not moving anywhere. And then the screw is now offset, so there's nothing, you're not trying to put a screwdriver in where the thread is. The bolt will be over here. Another thing, hopefully the camera will show it, there's a little, right down there, like a little cross shape. I got some square nuts, and so the square nut will slide in there, and then the machine screw will go down into the square nut. Nothing comes out the back. So the beauty of that is once it's bolted to some backplane like on the bike, you're still going to be able to do the tensioning without having to get around to the backside where you can't see and it's hard to work. So everything is now on the front. So you can do all of the tensioning and moving and everything from the front side. So let's talk about these holes. They are for the motors, right? So one motor in that one and then the smaller motor here. So my next test is to mount the motors to this, get all the tensioning system put together, mount this actually on a board as well. So they'll be on a board in a line like this. And then I'm actually going to hook up the transmitter and the receiver, and hopefully actuate and move the motors and watch the wrist move. So that's what I'm building up to. But anyway, those are the mechanical changes. And I think I'll end this video here and then start another one where I'm going to talk about some of the software things. Okay? All right, enough of this. Okay, motor discussion time. So I've showed this before. This is the tiny mover motor. So talk about how these things communicate. So they actually talk on what's called the CANbus. I forget what CAN stands for. But CANbus was created for the automotive industry, for cars. So as cars got more complicated, you would have all these different little gadgets around the car, a little motor, a little servo, whatever. What used to have to happen is all those gadgets, like 60 gadgets around the car, would all run wiring back to a central controller. And you ended up with a whole lot of big wire bundles. So CANbus allows you to daisy chain several of those little controllers together and then just run one pair of wires back to the central controller. And they all operate on what's called the CANbus. It's very reliable, as you would expect it and would need to be for a car. It needs to be super reliable. So Tiny Mover made the decision to communicate on the CANbus. Now let's talk about the receiver, the transmitter and receiver. So this is my receiver right here. This is a TD-R18 from Free Sky. This does not talk on CANbus. So think back to when I was moving the head, dummy's head up and down. That setup was basically a 12-volt battery hooked up to a 5-volt step-down transformer, because these run on, won't run on 12. So that takes the voltage down to 5 for this. And then pins 1 and 2, which are these first two pins right here, there were just servo cables that went directly to the servo. So as I was moving the stick, power going from the 12-volt battery through the step-down transformer, through this, right to the servo. And that's it. It's very simple. And then as I moved the stick, it was changing what they call PWM, pulse width modulating signal. And that's what the servo works on. These motors, though, like I said, they talk on CANbus. They won't accept a PWM signal. So what needs to happen is there needs to be some sort of intermediary between the receiver and the motor. And I'm going to do that with an Arduino. This is an MKR Wi-Fi 1010 board, you can put a shield, which is just basically another board that pops on top of that, which is a CANbus shield. So that's why I'm going to be using this. Now let's talk about back to the receiver. So each of these ports that you can plug a cable into can be configured in the FreeSky transmitter. You actually configure from the transmitter, you configure the receiver. Each one can be set to be PWM, F-bus, S-bus, S-port, and so one of those I'm going to configure to be S-bus. And why that's important is then all 24 channels will go out that one port, that one signal, and they will come into the Arduino. Now there's a couple of challenges associated with that. First of all, the S-bus is an inverted signal, so all the pluses are minuses and all the minuses are pluses. So you actually have to invert the inverted signal. So the invert of an inverted signal, is that just a vert? Anyway, that needs to be done. So you can do it a couple different ways. A friend, another builder, Neil, actually pointed me to these tiny itty bitty boards, which you have to do a little soldering on, which I was successful. And that has a couple of resistors and I forget what the other component is on it, but it inverts the signal. So that sends then a right side up, so to speak, signal to the Arduino, which can then be read by the Arduino. Now you've now got the signal into the Arduino, but it needs to be decoded. It's not that straightforward. There's not like, just easily separated signals. There's a little bit of math and bit juggling that has to go on. And I will confess, I did not write that code. I'm stealing it from somebody else. But anyway, that once the signal is in, you decode it and you get your information into the channels. Then with the Arduino, I can do what I need to do and send an output signal through the CAN shield and talk to this guy and hopefully move things around. So I'll be shooting a video. I've actually got this working, and I'll shoot a video showing that it works. So that'll be, I think, the next thing that you'll be seeing. Okay. All right. I said I was going to show some Arduino S-bus decode stuff, and look, here it is. So here's the setup. That is the transmitter. Back there, flashing blue, is the TDR18, and on the wires coming out of it, you see that little plastic thing? That is that itty bitty signal inverter board that I was talking about. And then we have the Arduino, excuse me, MKR 1010. And then over here, we have my Macintosh. So this program is it's all set up, it's all running right now. I'm gonna zoom in a little bit here. So you see these columns of numbers, that is the decoded, it's printed out in the serial monitor, the decoded signals. And so I have 5 of them actually programmed. So if you watch column 1, you see those numbers changing now because I'm moving the stick back and forth. So that is channel 1, channel 2, second column over, same stick. And then channel 5, that is one of the twist ends, twist end on the left stick, and then twist end on the right stick is channel 6. So, so that is successfully decoding the S-bus signal into Arduino, and then with those numbers, with that information, I can then program some movements. So one thing to note though, so I will put this code into my GitHub, and I'll put a link to the GitHub in the description. So one thing about this code It is built on an S-Bus library from Boulder Flight, which is a different manufacturer. I have FreeSky, but it works. However, it's built for 16 channels, and the FreeSky S-Bus has 24 channels. So eventually I will need some new software to do this operation. And another builder, my friend Neil, I volunteered him, let's be honest, to do that, and he's graciously probably gonna help me with it because he's a great guy. So anyway, I'll be doing some more videos showing this code as I start to make changes to it, to have it do more things, move things, that sort of stuff. So stay tuned. All right, there you have it. Mysteries of the CANbus revealed. All right, so we've got our S-Bus signal decoded into an Arduino. So the next steps are to write some code that makes things move, and then hopefully, well, not hopefully, hook everything up together, and then see if I can get that whole shoot and match to communicate. And hopefully we don't have one of those what we've got here is failure to communicate moments. So next time, see you later. This is a test. We'll see if I pass.